Cool. Now we're recording. So thank you for coming. Yeah, I've used a clickbaity title, The Dark Arts of Prompt Engineering. But my goal for today is to give you a fundamentals in what is in-context learning. How do you work with it? How do you make it beneficial for your own business or your own area of research, basically? And I will also be joined by Valentin, who is my teammate over there, who's done some really cool stuff with prompt tuning. And if the prompt engineering paradigm doesn't give you enough benefit, but you don't want to go down to fine-tuning models because it's too costly, then you can go in between. So. Okay. So the outline for today is I'll give you a brief history of large language models. I'm not going to go into the details, like that's what Tianzong did in the previous workshop. But I think it's important to run through the history so you understand the context of how we got here and why all of this today is, or how it's enabled, basically. And then I'll go through some prompt engineering basics, prompt design, and give you a few prompt paradigm ideas there. So, and then I'll hand it over to Valentin to continue. So, and what's out of the scope is the security aspects, this like prompt injection, that is going to be a talk by Ali, and also the agents, which is going to be a talk by Victor from Sana. And also the deployment aspects, which is going to come later on as well. So we'll have separate workshops for these. Cool. So before I go, I'll just introduce myself and introduce this lovely office and the company behind it. So I am a ML engineer working here at EQT Motherbrain. I've been here for 1.5 years now. I've previously worked in news media at Schibsted and also at Ericsson in telecom. And I built, I don't know, maybe 20, 30 different models. Out of these, maybe 6 or 7 have ended up in production. And out of these, maybe 2 or 3 are delivering like real true value. So it is a field with like a very high failure rate. But I find it super interesting. But I originally started as a Pascal developer back in like 2005. So I was building electronic design plugins and applications like that. So Pascal is very uncool these days. Everything is Python based, but that's where I started. And then I moved into telecom, where I was doing radio engineering. So I was deploying GSM, 2G networks, 3G networks, 4G networks around the world. Back then, I did basically what data scientists today do. So I was doing A/B testing. I was looking at correlations between parameters in a network and sort of the outputs of the network, like dropped calls, dropped throughputs, things like that. So we didn't call it data science back then. You know, you're just doing your work. But today that will be called data science. So, and yeah, so I started with ML around 2017, and I've got a few papers published, and I've got a couple of patents as well. So. It's yeah, not a like top-end OpenAI researcher, but I've done a few things, so that's nice. And yeah, EQT and Motherbrain. So EQT is a Swedish global investment company. It's a so EQT, we have a bunch of different funds, from ventures, which is focusing on like early stage startups, through to growth, through to private equity and infrastructure funds. So we're sort of across everything. The mission of EQT is to invest in companies and make them amazing. And Motherbrain is a special group within EQT that is essentially driving an AI strategy forward. So we're about 40 people right now. It's a mixture of user experience designers, full stack developers, machine learning people like myself and Valentin over there, data engineers, infrastructure engineers. So we have a kind of a full stack that's sort of helping us get along. Yeah, we're sort of dedicated to harnessing the latest and greatest AI, but we don't shy away from using the sort of uncool stuff if it delivers real value, right? So you can always fall back onto data science, classic data science, and classic machine learning as well. I might actually turn off the sound. Yeah, thanks. Or just no. I think it's the Sonos. If you turn off the Sonos. Now, perfect. There you go. Cool. Right. So a brief history of large language models. So I've given like a timeline here. I've compiled this timeline, and it's always difficult to find a starting point because science is a sort of a cumulative field. You can never start from a single spot. But I chose in this particular timeline to start with something called Word2Vec, which was back in 2013, developed in Czech Republic by a guy called Tomas Mikolov. And it's basically a very simple word embedding model. And the reason why I started with this one is because the modern day large language models are effectively doing exactly the same thing, but using a different architecture on a much greater scale and across a bigger amount of data. But the sort of the goals of the training and the strategy is to me very, very similar. Up until around 2017, the recurrent neural networks were sort of the staple of language or neural language modeling. They had a lot of limitations, so recurrent neural networks would take one word or one token at a time and sort of try to translate it or map it to something else. There would be some kind of a latent representation kind of going over time, but it was very sequential. It would sort of forget context after a while, so it had a lot of limitations. So in 2017, Google came out with something called Attention is All You Need, and it's a famous seminal paper right now. And the story goes that a Ukrainian, an Indian, and a German basically were standing around a coffee machine discussing how to improve a Google Translate. And they came up with this attention mechanism. And the Ukrainian gentleman, Ilya, he was basically inspired by Arrival. It's a science fiction film where there is aliens in it and they have a particular language. And the language is not sequential like ours, but actually every symbol is an entire representation sort of concepts. And so in one symbol, you basically attend to many different things. And that was inspiration for him to start researching into this. And out of this paper, a transformer was born. And the transformer is the building block of all the large language models today. So if you're using ChatGPT, you're using a transformer underneath. So in June 2018, OpenAI came out with GPT, the very first GPT model. It stands for Generative Pre-trained Transformer. It's what we call an autoregressive model or a decoder-only model. It's basically the birth of real sort of generative large language models. So this was a true generative model in a sense that it learns how the text or the data underneath was actually generated, how it came to be. Google came out with something called BERT, which is not a generative model. It's an encoder-only model, but BERT was used, I think, all the way up until ChatGPT. It's been a kind of a staple of representing language and text. Then in 2019, GPT-2 came out from OpenAI. So what happened between GPT-1 and GPT-2? They just gave it more data and made the model bigger. And all of a sudden, GPT-2 could generate incredible text. It looked like an actual human-generated text. It looked really, really good. It was complete nonsense, but the feeling of it was that it was human-like. So they decided, okay, let's go step this up a notch. Let's make it even bigger, give it even more data. And then GPT-3 came out. And here, all of a sudden, something new started to happen. So all of a sudden, you could use this model to basically reason. So you could supply the text with some examples, and the model would know how to, for example, continue from these examples. And it's what we call few-shot learning. So this was amazing. Up to this point, you had to take models and you had to fine-tune them on specific tasks. Like if you want to classify pieces of text into different categories, you would have to take a BERT model and do some fine-tuning on it. Now you don't have to. Now you can actually give it some text, and implicit in this text is something that tells the model to do, basically. And then a whole bunch of other things appeared afterwards. So on your right-hand side here is one of the diagrams that showed something called the emergent behavior, which I find super interesting. So what happens is, if you scale the model up to a certain point, on certain tasks, you get random predictions, like it's just behaving randomly. But after a certain point, it actually starts to behave very nicely. It's actually giving you correct predictions. So basically, what we have is the model itself, or its ability to reason, is sort of a function of energy, how much energy it spends, essentially, which was very interesting. And then later on, we had a few more things, which was this ability to instruction tune or do this supervised fine-tuning on models. So now you're giving it additional data where you actually put some instructions into it, like, for example, classify this text or summarize this text and so on. And also another thing called reinforcement learning with human feedback. And this thing called reinforcement learning with human feedback is what aligns the model with sort of human preferences or human behaviors. All of this now accumulated into something called ChatGPT, which was released by OpenAI about 12 months ago. And then after that, the whole world changed. So, right. So out of all of this, we have this concept of in-context learning. So these autoregressive models like ChatGPT or GPT-4, they really, really want to generate or output some text, okay? But they are contextual, so you need to give them some sort of a context, so they know. If you don't give them context, they'll just generate random things which sound very nice, but they're completely random. But if you give them context, you give them focus, basically. And if you also give them instructions, then they will start executing these instructions, which is incredible. So in order to steer all of this, you basically create something called a prompt. We call it a prompt these days. So the prompt consists of a context, or I mean, it can consist of one or more of these things. So it can consist of a context. In certain APIs, we call that a system prompt. It can consist of instruction, which is sometimes referred to as user prompt. Input data, so if you want to give it some data that it can work on, then we can give it that. It can be some text, it can be, these days, it can be an image, it can be a PDF file, a PowerPoint presentation, it can be almost anything these days. And then you can also specify an output format, like how do you want the model to generate the output? Do you want it to be text? Do you want it to be a PowerPoint template? Do you want it to be a JSON, an XML? It's completely up to you. So depending on these elements, you basically, the model sort of activates different sampling behavior underneath. So it's generating text in a different way. But the output is never deterministic. So one thing that you should all know is that these models are stochastic. So they are, everything is about probabilities. And you can never steer it so that it's fully deterministic. Like you can never give you the exact output every single time. It's just not possible. So we have the prompt. So of course, we have this new discipline called prompt engineering. And everyone is, these days, a prompt engineer. If you use a ChatGPT at home, personally, or as part of your work, you're a prompt engineer in a sense. So some people call it a discipline. I like to call it more as a skill set. So it's a little bit like being able to work with spreadsheets. I mean, there is like spreadsheet World Cups, I think. There's an Excel World Cup that's held every year. But usually you're not, your title is not like a spreadsheet specialist. You are an analyst or a data entry, and you use Excel or Google Sheets as your tool. And it's the same here. So a prompt and working with prompts is just a sort of a tool that's going to become part of everyday life. But there is a discipline called AI engineering that's sort of emerging, which is more kind of a full stack developer that's more focused on integrating prompts and LLMs sort of together to give some sort of business value. I'd like to think of it when you're working with prompts, you're basically leveraging a lot of different skills. Like one is a language understanding. How do you phrase things in a particular way? Maybe this whole paradigm is going to make us really good and very efficient writers. So it sort of forces you to be direct and not overly verbose to give it the right kind of information. And that usually gives you the best results. And the aim of prompt engineering is to basically, out of this stochastic, unpredictable model, to kind of have some sort of a pseudo-deterministic output that will generate value for you, right? And that you can use in other applications. Okay, so when you work with large language models, you are faced with a lot of parameters that you can try to control. And a lot of these, so if you use ChatGPT, I don't think you can really manipulate any of these. But if you use APIs to talk to, for example, OpenAI's models, or if you're using these open source models like Mistral or Llama, then you can usually specify these. So you have, and I've grouped them into 3 categories. So the one category is for controlling the sampling behavior. So how is the text being sampled from these models and output? And you have kind of 2 things that you can tune there. You can choose to tune the temperature, or you can choose tune something called nucleus prompting, or nucleus sampling, or top P. So the temperature controls, you can think of it like temperature, like a real thing. Like, temperature is just basically molecules smashing with each other. So if you increase the temperature, you get more heat, right? And then you get more kind of randomness happening. So if you turn the temperature down, you are supposed to get more kind of deterministic sampling happening. But again, not guaranteed, okay? So you should not be fooled into thinking that if you put temperature to 0 or some very low value, that you're going to get deterministic output. It's not going to happen. The other one is the top P, which is more like, if you give it 0.1, for example, basically the tokens that are in the sort of the top 10% will be sampled more often, essentially. Then you have seed. This is a fairly new concept, which is also very misguided, I would say. So seed, usually when we talk about random number generation, if you give it a seed of, let's say, 42, you're always going to get the same numbers coming out. So this is meant to be the same thing, but again, it's not fully deterministic. Then you have output diversity. So you can have penalties on the output. So you can have presence penalty or frequency penalty, which basically control how often different words occur in your output. So you can kind of try to control this so that you get more diversity, so you get newer words coming out. Or if you want something a bit more quasi-deterministic, you can lower these penalties, or actually increase them. And then you have also the stopping conditions. So you can stop the LLM from generating too much text. If you say, right, I want you to stop at maximum, 300 tokens, which is, 200 something words, basically. You can also specify a stop sequence, like I want you to stop generating text when you see this sequence of characters. So this is all the different things that you can kind of tune and control. Okay, so now the sort of the fun stuff, which is the basic prompt design. Let's see, maybe I could just do a quick demo. Let's see, let's try this out. Can you still see the screen? Yep. Beautiful. So we go into, you've all seen this, right? Okay. Let's see. Let's go to Aftenbladet, which is my previous employer. And let's just find there you go, this is relevant. Cool. So let's just copy paste this. And so I'll give it an instruction, okay? So you sort of start off with an instruction. You think in your head, what kind of instruction do you want? Right? I want two instructions. I want translation, because that was Swedish text. I want to translate it to English. And I want a summary. So I wanted to summarize the text for me. So, so I'll do this. Step 1, translate the text to English. I'll say translate the provider text. Step 2. And this is another nice thing, to give it steps, so it knows the sort of sequence of actions that it can take. Provide the, let's say, 1 to 2 sentence summary of the translated text. Okay, and say Swedish text. Paste it. English translation and summary. Let's see if it works. So there you go. So it did exactly what I told it to do. So it the article is in Swedish. There seems to be bad weather over Skellefteå kommun. All the buses from 6 o'clock till 7 in the morning are cancelled. It's being reported by this particular Swedish news channel. And that's exactly what it translates, and it gives me literally 2-sentence summary. So this is working with prompts, basically. So, like I said, useful to think in terms of what task does it need to perform. So is it summarization, information extraction, etc. And then the rest of it is all about like molding it in a particular way, giving it enough context, enough data, and telling it how the output should be generated. I could have told it to generate JSON output with particular fields, so that I could, for example, as a developer, I could build an API that could ingest that and then get like translation and a summary of that article, and I could build a whole service on top of that. I can chain that to other things like audio or text to audio, and so I can do a lot of things with this. So that was kind of what I showed you, the summarization. This is one of the examples. Another really good one is like information extraction. So if you have a lot of text and you're trying to extract particular type of entities, you can do that very easily here. In the past, you had to use pretty complicated models to extract entities. Nowadays, you can just tell it what you want. In this case, you ask it, mention the large language model-based product mentioned in the paragraph above, and it actually identifies it as ChatGPT. Question answering is another big one. So you have a lot of text, and you want some things answered there. You can do this for all kinds of reasons, like fact checking, or just sort of if you don't want to read through a lot of text, you want to get answers pretty quickly. You can do that as well. Text classification as well. So it's like in this case, it's a sentiment analysis. This is an example of a few shot. Oh no, actually, this is a 0-shot prompting. So literally, you're giving instruction, classify the text into one of 3 categories: neutral, positive, and negative. You give it a text, and you tell it like, what's the sentiment? You can do a few shot as well, where you give it a few examples of what neutral is, what positive is, what negative is. So you can kind of bootstrap the model so it understands better. And this is a really popular one with developers, engineers, where you're actually doing code generation. So you can tell it, in this case, you're telling it to create a MySQL query based on these tables, departments and students with specific columns, and literally generates a piece of code or a SQL query that you can run, and it works quite well. And there's a lot of sort of coding co-pilot tools that are out there now using this this technique. Cool. And then we have some interesting things, like if you want to go a little bit more advanced. So this is pretty simple stuff. I think a lot of people can do this and play around with it. One thing that we've also used here, and this is Ville, my my boss, that also loves doing this. It's basically where you specify references. So if you're telling it to answer a particular question and give you something from a large body of text, you tell it to also provide attribution or a reference. The interesting thing is if you tell it to provide the reference first and then give the answer, it performs better. So what tends to happen is if you tell it to give you an answer, provide a reference, is it gives you the answer and then it makes up the reference. It kind of hallucinates the whole thing. So, whereas the other way around, it tends to work. Again, it's not deterministic, so it's not gonna like work every time, but it works better. Then the other thing you can use is to get it to adopt a persona. So, you know, you're telling it, hey, you are a partner in a ventures fund, or you are a human resources generalist. So you're kind of bootstrapping the model underneath by giving it a role to play, so you can focus on more specific things for that role, which is very, very handy. And then, like I showed you before in a summarization and a translation task, like you can split a more complicated task into multiple steps, and that always works much better than just kind of giving a general statement. There's also this concept of using inner monologues, which is very interesting. So you can get the model to talk to itself. So tell it like, okay, here first you are thinking of a translation. So how would you do that? And then you kind of give it like quotes so you can fill that in. And okay, now you got the translation. So how would you now think of a summary? And you basically telling the model to kind of talk to itself. Then a really interesting one is this emotional stimuli, which is here at the bottom. So this is a paper that came out like a few months ago, very interesting. So if you tell the model to be a little bit more emotive, so in this case, what they did was they modified the original prompt. The original prompt was determine whether an input word has the same meaning in the two input sentences, okay? So it's an instruction. And they got a particular performance using this instruction. If they just now added an additional sentence saying, this is very important to my career, the model performs much better, like visibly much better. So very, very interesting. So if you wanted to perform better, you kind of make it feel bad. So the other thing that came out like just a few days ago is something called System to Attention, which is from Facebook or from Meta, which is you basically you use a prompt to generate a prompt. So let's say you have a large body of text and you're trying to extract some information from it. There could be a lot of sort of spurious correlations in that, or a lot of noise. And what you do is you create an instruction to get rid of the noise, just focus in this particular thing, entity or an event or whatever you're trying to extract, and produce a prompt specific to that. So it'll probably produce a much kind of clearer prompt that then you can use to get to the actual answer. And again, it seems to work extremely well. So this whole area, all of these kind of hacks or whatever you want to call them, is like an active area of research. No one really knows, exactly how it works, but one way to think about it is that what is the data that was used to train all this? So, for example, it's forums, it's threads, it's people talking to each other, it's Wikipedia pages, it's basically the whole internet. So you have to think about like how is the data generated on the internet? Like how do people talk to each other in forums, in threads, in Stack Overflow? How do people write information or sort of pieces of information about different things? So if you think of it that way, then try to sort of step into the shoes. So another thing I saw recently is that you should never treat the model or treat the prompt as a you, like you should do this, or you should explain your reasoning for that. They say that you should treat it from a third person point of view, like he or she should explain the reasons. And because a lot of these instructions, if you look at like the data on the internet, people are kind of, I don't know, narcissistic, or, a lot of the time you don't explain yourself on the internet. You don't go like, oh, I got this wrong, because, most often, like the most highest probability is on someone saying he or she got this wrong. So yeah, so basically you have to kind of step in the shoes of the data that is underneath it all. And then you get some interesting results happening. So few-shot prompting, I've talked a little bit about that already. The interesting thing was really this GPT-3 when it came out. And that paper, I think, it's called Language Models Are Few-Shot Learners. So what they found was that when they just scaled the model, when they made a bigger model, you could actually get much better reasoning from just giving the model a few examples. So you say, I can actually show you. It's maybe much easier. So let's do some few-shot. So let's say this is a kind of relevant task in EQT or anywhere where we're kind of looking at businesses. So you can say categorize the following companies into specific industries. Okay, so you give it an instruction. Now I'm going to give it some examples. Let's say Telia. Telia is telecom, right? Volvo. Automotive. It'll actually probably, I'm going to try that with the spelling mistake as well later. Okay, telecom, let's say Zara, retail, okay. H&M. Retail, fashion retail. So, it's very cool. We've used it in the past for sort of kind of trialing or prototyping this sort of weak supervision. So there is a concept of weekly supervising or labeling things. There were many frameworks in the past. Snorkel, I think, was one of them, where you sort of use Python or regular expressions to sort of generate labels for things, and then you build your own models based on these labels. But you can actually use also large language models to do that as well. So that's very, very handy. Okay, but yeah, it's got limitations to it. Sometimes it sort of just doesn't have enough information in those few examples. So what we tend to use is also chain of thought prompting. So in this case, you try to break down a very complicated task into sort of multiple steps, and you're giving it the reasoning along the way as well. So in this case, what happened was, like, there was a question as a sort of a maths question, and there was just the answer. So this is like an example that was given to the model, and now there's a new question, and you're expecting another answer there. In this case, the model answered 27, which was incorrect. But if instead you give it, as an example, you give it a question and the answer, not just the actual answer, but the reasoning of how it came to that answer, that seems to work much better. So then when you give it another question, it actually makes the reasoning steps as well, and it gets to the correct answer. Very interesting. Again, possibly related to the underlying data underneath, where the majority of data has a lot of verbosity to it. So there's, if you go to Stack Overflow, where people are writing sort of coding questions, you know, people are not going to give you just like, it's this. Oftentimes it's more verbose. There will be more explanations and reasoning descriptions. So the data underneath these models is kind of telling you that you should be also a bit more, you should specify these steps. And yeah, this one, retrieval augmented generation, RAG. RAG is become sort of a staple of applying large language models in businesses now. So pretty much if you see any business that's doing like a cool AI on top of LLMs, they're probably doing RAG under the hood. So RAG started from Facebook, and it was actually an explicit model that was built. So the model consists of something called a retriever and a generator. So you basically train the retriever, or they're trained together end to end, but essentially what you want is you want the retriever to get you the relevant information and a generator to give you the answer, a nice answer. Nowadays, people don't really do that. They just use OpenAI or ChatGPT or large language models without training. So what they do is first they chunk and encode and index the text or the documents or their knowledge, right? They store it into a database, a particular type of database called a vector database. Examples are, for example, Pinecone is one vector database. This encoding or encoding into this database is done through something called an embedding. And one example is an ADA2 embedding from OpenAI. And then let's say you want to retrieve some information. So let's say you want an answer to some question. You encode that question as also as an embedding, and then you do an approximate neighbor search across this database. So you do a vector search. You get the most relevant, let's say, 10 pieces of information, and then you feed that to ChatGPT to give you a single answer, basically. Yeah, it's efficient in the sense that you don't have to train big models anymore. You can just kind of glue things together. You still need to sort of index your data and store it into a vector database, but that's becoming easier and easier all the time. You maintain the up-to-date knowledge of your business. So if things are changing in your domain, you're getting new information, you just store it in a database, and the model will be able to stay up to date. Also it tends to reduce hallucinations because it's now dependent on more recent, fresher knowledge that's external to the model itself as well. But again, there's no guarantees, so it might still hallucinate, but you just reduce the chances of that happening. And there's a lot of tools that we used LangChain in the past. Nowadays, OpenAI has this GPTs and Assistant API, which actually does the whole thing for you. So it does if you give it a PDF file, it'll literally chunk it, put it into a quadrant vector database, and every time you type something in it, it'll literally do that retrieval from the database and then give you the answer. So it's all done automatically for you. And I think this is the last part. So the evaluation. So how do you evaluate all this? Like how do you know if it's doing good or if it needs more work? And this is really tricky. I mean, this is first of all, we're dealing with a lot of subjective information. Like if you're trying to, let's say I had one question earlier about the CVs. Let's say you're trying to create something that can parse a lot of CVs from people, resumes, and map them to the right skills or right jobs, for example. It's, how do you evaluate this? Like how good is it? It's very difficult. You have to manually look at it, and you have to sort of subjectively look at it and go, yeah, this is probably okay. It's very tricky. So this evaluation and also the fact that these models tend to hallucinate, like I said, they're not deterministic, so they will give you hallucinations. They will just they are born to generate text. Okay, so that's what they want to do, and they will do that. And it's just a question of whether the text is useful to you. So that tends to sort of erode a bit of trust and a bit of safety when you're working with these things. There are some efforts to provide some more systemized way of evaluating them. We were in touch with people from Watchful in the past. They've got some really interesting ideas happening. They've got this concept of structural and conceptual uncertainty. So they have a way of measuring that using information theory. Conceptual uncertainty is like when the model isn't sure what to say, and the structural is if it doesn't know how to say it. And they were able to kind of plot that and give you an idea of like how far off the model is gone, basically. So it's a very nice way of tracking and saying, hey, this is not working for me. This is like gone way off track. And then for RAG in particular, there is a RAG-as framework from Exploiting Gradients organization, where they also have some kind of metrics built in, so you can sort of evaluate the relevancy of the answers, the precision, and also what they call the faithfulness as well. So there is work ongoing, but it is very tricky. So oftentimes you have to sort of roll up your sleeves and qualitatively evaluate whether the model is giving the right thing. Cool. And I think that's all from me. Are there any questions, or? It's very quiet, so I don't know if it's. I've got the microphone as well, so if you got questions, yeah.
Why did you have to give those examples for the few shots? You gave some examples.
Yeah.
What was the reason?
It's more to put the model into the frame of mind that it's mapping a particular kind of taxonomy of industry categories. Mm-hmm. So that was just a few examples. It was just a toy example. If I wanted to do this properly, I would specify a taxonomy beforehand. So I would say, these are the industrial categories that I'm interested in, and provide a list, and tell it, I want you to pick a category from one of the categories from this list, or if you don't know, just say don't know or unknown, and then I would give it a few examples. So that's a more kind of a structured way of doing it.
Thanks.
Yeah. Thanks, Armin. What's your take of Kill Star? And
no idea.
You cannot skip.
No idea. I've got no idea. It's just. I think it's 4chan stuff, right? So, yeah, don't know.
So when you use RAGs, so you have a documents, and then RAGs will give you some context from the documents, and that's what you put in ChatGPT. So in such case, this model, will it constrain itself to the context only, or will it use that context in addition to what it is trained on?
Yeah, it doesn't have to constrain itself. So it really wants to generate some output. So there's always a probability that it'll look within itself, so to speak, and find some new and maybe potentially unwanted things to say as well. So you can never guarantee it to completely constrain itself to what it's retrieved. Yeah.
This is a very new area, and there's a lot of hype around it.
Yes.
Can you hypothesize what might be, from a regulatory perspective, potential areas that governments might try to limit this technology? What kind of dangers do you see?
It's many. And yeah, hopefully we'll have a more deeper analysis into this after this sort of EU AI Act comes through, and there's like a bit more certainty over where things are heading. But I mean, it's an absolute landmine, from spitting out private information, because again, these models want to generate output. if somewhere in there, in the model weights, there is personal information hidden away, it may come out. You cannot guarantee that it will never come out. Even though you can try to design prompts in such a way, you still can never guarantee that. Copyright information, if it starts generating stuff that's actually copyright or there's intellectual property on it. Obviously unsafe things like biases towards particular groups of people. It's just an absolute landmine, you know. So I see a lot of problems. So it's more about working with it in a specific context. So like some of the examples I gave, like classifying categories, summarizing text. So, you know, being able to narrow it down to a particular use case in a safe environment as well. I think that's the best way to work with it at the beginning.
Yes, thank you so much. And
No
again,
worries.
thank you for the presentation. It's really insightful.
Thank you.
And for me, I think I have two questions.
Yes.
The first is that because I was working in the customer support team in a company, and there was a need to develop how can I say, domain-specific chatbot based on the LLM. And as you mentioned, the LLM evaluation is really tricky, but thanks to the open source platforms like Hugging Face leaderboard, we can have some good enough evaluation tricks. But as for the evaluation methods for domain-specific ones, especially in the customer support team, customer support domain or other domains, we at that time felt a little bit tricky to design those evaluation methods. So I'm wondering if you have any insights about that. And my second question is, maybe it's a really high-level question, like how do you see the future of all the, how can I say, middlewares of in the area of LLMs, such as LangChain? Because there are some people on Twitter, they are saying like in the wave where LLM is sweeping all over the world, the people that procrastinate wins, because some people, they just dive into the technology of RAG for 6 months or even more, but now OpenAI has assistant API and kind of kill LangChain in some way.
Yeah.
So yeah, this might be a really high-level question,
Yeah,
but
no,
yeah,
it's,
just really curious about your opinion. Thank
Very
you.
valid questions, yeah. So the first one, I personally don't trust the sort of the leaderboards and things like that. They are good to get a very rough understanding of where the models are, but if it comes to applying the model LLM in your own domain, you literally have to define your own validation set. I don't think there's any better way. Basically, I wouldn't trust them. And I'm saying this because I've tried, I don't know, in the last few months, I've tried maybe 15 different Hugging Face models, and I get very, very strange things. Like there was one model where it was meant to be state of the art in understanding both text and images, and I gave it an image of a graph, a chart, a bar chart basically, and told it to summarize the bar chart for me. And it told me it was a tennis player playing tennis. You know, so it's like, but if you look at the score for this model, it's pretty high on the leaderboard. So it's yeah, you have to do your own work there. The second one, I mean, it's like super volatile, and I think I've told this before, but it's like if you build, you have to think about if you're building a feature or if you're building sort of a product that's doing something novel. But the area is very volatile, very sensitive. I mean, when LangChain came out, we used it. We built things using LangChain, and LangChain was fantastic. And we hooked it up to Pinecone database, and we did all kinds of cool stuff. But now you have like Assistant, and that does everything for you. So yeah, I can't like foresee what's going to happen next, but you can think if it's going to add more context or make things easier to work with, it's very volatile. So it's more if you're thinking in terms of something completely new that companies like OpenAI don't, need to focus on. So it could be maybe some sort of a domain adaptation for certain businesses and things like that. But it's very, very tricky. So,
yeah. You seem to be very interested and into LLMs, which is super cool.
Yep.
And you might have answered it with your last answer already, but I was wondering how much LLMs do you use at EQT and especially in Motherbrain without telling too much? Like, is it more you use it for developing, or are you actually experimenting with LLM models as part of the core feature of the product?
Yeah. I'll be completely transparent. No, there's no secrets here. So Valentin is going to present work that he's did with LLMs maybe after a short break. So you're going to find out a lot of details there. We have, like everybody else, we have our own chatbot that was built by Ville there. So it's on our platform. So it's meant to, if some of our users, investment teams, they want to work with, for example, they want to find out information about previous investment deals, they can use a chatbot to kind of get a quick summary, get some descriptions. And again, that's a RAG with chain of thought reasoning, React framework. There's all kinds of little things baked in. It's using LangChain as well. Then we have much kind of simpler tools where we use embeddings. So we use just OpenAI embeddings to just do quick similarity search and recommendations. We do some quasi-hide. I don't know if you've heard of hide, where you basically, you have a question, you want an answer to the question. So what you do is you use hide to essentially generate a hypothetical answer, and then you use that hypothetical answer to search across the sort of the database. This is what we call like an asymmetric problem. So when you have a question, it's typically very short. It's like a few words, but you are interested in the answer, which is maybe a document, which is a lot of words. So it's very asymmetric. So by generating a hypothetical answer, you get that better symmetry and you get slightly better improvement in retrieval. So we use that as well. There's tons of stuff. Even way before ChatGPT, there's Lele sitting next to Valentin over there. I mean, he used T5 model from Google to create a sector prediction framework. He even had a paper published at IGCAI. Yeah. So yeah, we're pretty transparent about it. But we use LLMs a lot. So, but I have to confess that modeling aspects are. I mean, the OpenAI ecosystem is getting so strong that a lot of the focus is also sort of shifting on very quick sort of wins in using that ecosystems as well. Sorry, if we want to do quick wins, like if we have some very specific use cases, we don't want to invest huge amount of time in building models from scratch. We find that some of the things from OpenAI can sort of help us get there much quicker. So.
I wanted to ask, earlier, when ChatGPT just appeared, there were a lot of people trying to make it say offensive stuff or stuff it wasn't trying not to say. Yeah. And then the workaround was to create a hypothetical scenario oh, I'm an author who has to say that, or we're in this situation, and that would work. So do you know which feature of this model that caused that to work, that trick to work?
I think it's like a system prompt. So you're kind of giving it a role to play and trying to confine it. I don't think you can still guarantee that it's not going to do the thing, but you can use a system prompt to sort of bootstrap it and say, hey, you should not do this, you should not say that. And so there is also a new concept of guardrails as well. So there is this, there are frameworks out there. I think Nemo guardrails is one of them, where you also try to restrict the model in terms of what it's allowed to say or how it's allowed to say it. So, so look into the guardrails frameworks. They might be helpful.
Thank you.
Okay.
So I'm a co-founder of a company called Plusa, where we use Gen AI as a mental health coach for parents. And we're doing a Vinnova project at the moment where we're evaluating the AI coach versus a human psychologist. And I thought it was intriguing when it was said that we shouldn't give the AI a persona as a you, but rather as a third person. Like, could you give a little bit more of an example of how you would use it to give it like a psychologist persona, for example?
Yeah, it's more in terms of when you want to explain itself. So if you're doing this like iterative process with let's say ChatGPT, so you tell it to, okay, can you, what is the answer to this question? And you give it some background information. And it gives you the answer, but the answer is incorrect. And then you tell it, okay, you made a mistake, can you explain your reasoning to me? So it's more like you can give it like, assign it a name, like you are, I don't know, Emily, and Emily is giving me an answer to this question, and here's the question, and then Emily responds, and then okay, but Emily got it wrong, so can Emily please explain to me, so it's like that, so giving it a third person.
Yep. Yeah. Thank you.
There was one question here, he's trying, and then I think we should probably take a break then, and then let Valentin also do his presentation. So.
Curious if you've done any work here with using LLMs to build agents. If you have any just general talk on that. For example, I read this paper, Voyager. They used LLMs to build a Minecraft agent. And just curious if you have any feedback on LLMs in combination with RL or supplanting RL in any way. Yeah.
Okay. I haven't used it personally. I think maybe in the next workshop we're going to have in January, Victor from Sana is going to, I think, talk about these aspects. I've seen some work out there, like there was, it was almost like, I think it was a game where it was these agents, which were LLMs, kind of, playing this game against one another. Which was interesting. And I think I've seen also like a social media network, like a Twitter thing, where it was agents having different personalities and they were making tweets and then they were resharing and and I think in that experiment, they all converged. So they all just loved each other, basically, which was fascinating. Kind of, they just went in one direction after a while. But yeah, explicit like RL with LLMs, I don't have a lot of experience there. So, yeah.
Can I ask one more question?
Yeah, sure.
You mentioned Pinecone, where we're implementing RAGs at our company. And yeah, we're looking at all the different vector databases. We don't really have a good reason to pick one over the other. Do you have any? Is there a reason you picked Pinecone? Or?
I think Pinecone, we had a sort of because it's a managed system, so it's very easy. I think it was just very easy to work with. But the one that OpenAI and also XAI, which is Musk's new company, they use Quadrant, and I think that's an open source one. So you can have a look at that as well.
Thank you.
Yeah. Cool. I think we ended here. Should we have like a 10-minute break? Do you think? Just can go to the bathroom and then Valentin will continue with his presentation afterwards. So, thank you. Thank you.
Test. Good.
Do.
Hello, everybody. If you're ready and take your seats, we can continue with the next part of the session. Amazing. The next part of this talk will be a little bit more technical. Is it normal that I hear myself later than I speak? Okay. It's very confusing. I never had to use microphone before. Yeah, but I will present work that I did during my master thesis, which I wrote here at EQT. And I worked on a pipeline, basically, that Lela has worked on before, which was what Armin already talked about earlier, about a pipeline where we used the T5 language model, which was from Google and is similar to ChatGPT. And he used it together with prompt tuning and full language model fine tuning to create the sector classification pipeline. And in my master thesis, I did a research project where I built up on that. But first, let me introduce myself. I'm Valentin Buchner. I did my studies in the Netherlands. So during my bachelor, I did a minor in data science and artificial intelligence, and I enjoyed it a lot. And it felt to me like playing with Lego bricks. So then I continued to do my master in artificial intelligence. And next to that, I also worked at Landscape, which is a data consultancy. And I worked on a lot of natural language processing projects there. And then I had a privilege to come to EQT to work on my master thesis, which is about prompt tuning of large language models. And first, in this talk, I want to give some background knowledge, first of all, about what large language model fine-tuning actually is, and about something that's called parameter-efficient fine-tuning, which is a way to improve normal language model fine-tuning. And then I wanted to introduce my master thesis as a case study on how this can be done. Yeah, let's start with large language model fine-tuning. A lot of you have heard about that before, probably, especially since it's quite easy to do nowadays with OpenAI integrations. And basically, it's what you do when you want to optimize the performance of the language model on your specific data. Because often, while the language models are very good at answering very general questions, they often are not so good yet at very domain-specific questions. For example, if you work in finance, where you use a very certain kind of language. And also sometimes you have very specific downstream tasks. For example, you want to, let's say, classify what Armin showed earlier, right? You want to classify companies into their industries. And we know that fine-tuning can be very good at improving these, but there are also a lot of disadvantages to fine-tuning, which people are often not aware of. So first of all, there is the risk of catastrophic forgetting. It's basically that OpenAI and Facebook and Google and whoever develops these language models, they put millions of dollars into pre-training this, into having them learn a lot on a lot of data, and making them also very generalizable so that they are able to speak a lot of languages. And also, they also spend a lot on making sure that they are not biased, that they are not discriminating, that they are not insulting anyone. And once we fine-tune the large language model, we change the language model parameters. And I'm not referring to the hyperparameters that we can actually set sometimes, but I'm referring to the parameters that are stored within the language model. And once we change this, we risk that we forget all of this, what it learned, so it's not able to speak. Let's say we only fine-tune it on English language data, it might not be able to speak other languages anymore afterwards. And if there's some toxicity in the data set, it might start to also be toxic. And that wouldn't be very good for some kind of model that interacts with people. And then, of course, we know that it can also get very expensive. First of all, to train it, but then also if you want to train 10 different models, you also need to store them somewhere. And here's an example. I'm not sure if you can read it, but it's about someone who fine-tuned ChatGPT on Slack messages, and then you basically get a model that responds like people on Slack, but is absolutely not helpful anymore. Exactly. And one way to help out here is parameter-efficient fine-tuning, which is a technique where you basically only fine-tune a small subset of the model parameters, and you leave the rest of the model parameters untouched. And here we can see on this graph that exactly. So the orange and the red line is when we fine-tune the complete model, and the green line is when we use a parameter-efficient fine-tuning technique. Is it only me who hears the peeps? Is there something I can do about it? Oh, it's the speaker. Okay. And we see that the green and the orange and red lines are very close together. And when we have a model that's large enough, they're even the same. So with this parameter-efficient fine-tuning technique, we can achieve the same performance by only fine-tuning a very small subset of parameters. And for reference, also comparing it to the earlier talk about prompt engineering, it's the same as prompt design. And we see that it also achieves good performance, but not the same as if we fine-tune our model. And then here to the right graph, we can see actually the number of parameters that we need to change for different techniques. So again, prompt engineering, prompt design is all the way on bottom because we don't change any parameters. The model parameters stay untouched. We only change like how we talk to the model, right? And then we see that prompt tuning only uses between 0.01 and 0.001% of the parameters. So that's only a very small amount. And then there are some techniques that use more parameters, and full model tuning obviously uses 100% of the parameters. And first, this was developed to basically save computation, because if we update less parameters, we also need to calculate less. We need less computers for less time. It's better for our wallet and for the environment. And however, then when people started doing it, they realized there are also a lot of other benefits. Most importantly, that we don't forget what the model learned during pre-training, because if we don't change the model parameters, of course, we don't forget anything, which means that we can still speak other languages, and we can still have a model that doesn't start insulting people or so. One disadvantage, of course, compared to prompt engineering, is that we need to have a fine-tuning data set. So that means we need to have examples of input and output that we would, where we want the model to learn that this input should result in this output. And that we don't always have. Sometimes we need to generate it first. Sometimes we have to, we have to buy it from data vendors or so. And there are a lot of different parameter-efficient fine-tuning techniques. For example, LoRa, prompt tuning, IA3 are very popular, but I will talk about prompt tuning. Exactly. Let's introduce the problem that we actually had at EQT, which relates to thematic investment. And that is basically that we identify interesting macro trends that we know will be more important in the future. A very simple example, for example, renewable energy or circular economy. And then we want to find the companies that benefit from these macro trends, so we can invest in these companies. And if we formulate this as a machine learning problem, we can take a company, we can take, for example, the description that it has on LinkedIn and some keywords that we get from PitchBook, for example, and then we want the machine learning model to predict one or multiple sectors, industry sectors, that this company belongs into. So, for example, we can have this information about a company, and we want to predict these sectors. So it's actually very simple, a multi-label text classification task. But that actually itself already exists for a long time, but we had some additional challenges here, which is why traditional methods wouldn't perform very well. One is that we didn't have so much data available. So we had only about 5,500 examples available. And it's very difficult to create more data for that, because actually our private sector taxonomy is very difficult. It takes a lot of thinking to think actually where should this company go in the sector taxonomy, and you need help from investment professionals. And yeah, it's not an easy task. And also the framework changed a lot of time. So sometimes we add a sector or remove a sector, or we merge two sectors. Sometimes also we generate more training data. And in all of these cases, we want to retrain the model. So if we would fine-tune the complete model, but we would have to do it every month, that would not be very feasible. Also, we have a large number of different sectors, and it's very imbalanced. So here on this visualization, you can see the size of the sector in relation to how large it is printed on here. So we can see that about 5 sectors are printed very large because they occur in the dataset very often. But most of the sectors we can't even read actually, because they only occur very few times, maybe about 20 times. And normal machine learning models have a lot of difficulties learning from only 20 examples. And then we also have a very large inference data set of about 10 million companies. And if we would feed that to ChatGPT, it would take a very long time until we have all our predictions. Yeah, and all of these challenges eventually led us to try out how prompt tuning would work on this problem. And to explain prompt tuning, actually, I first want to explain how language models usually work, so we're all on the same page there. Basically here, we first have a description of company as an input, and whenever you type anything into ChatGPT, what it first does is that it tokenizes what you typed. So usually one token is one word, but sometimes also it splits them up. For example, if it doesn't know the word, or also if you made a spelling mistake, it splits them up into individual tokens. For example, that it basically splits it up in those tokens where it can best infer the meaning of. So like we can see that Vinted is split up in 2 different tokens. And then for each token, the language model has stored an embedding vector that it learned during pre-training. And then it retrieves this embedding vector for each token, and it stacks them on top of each other, which means that we have a matrix. It's just one matrix of a lot of values. And then we feed this matrix into the language model, and there happens a lot of matrix multiplications, nonlinear activation functions. It's just like a neural network and very, very large. And then we get a prediction out or an answer to our question. And now I just move this to the right, so nothing changes here. And now I add the prompt tuning. And it's a very simple addition, which is basically that we add a matrix that we call the soft prompt, and we concatenate this soft prompt with the embedding matrix that we got from the input, and then we feed both together in the language model. And then the same happens as before, only that we have this additional soft prompt. And if we draw the parallel to prompt engineering, this soft prompt kind of serves as instruction to the language model what to do. Just that it's numbers. So for us humans, it doesn't have any meaning. We can't translate it to our language. We doesn't know what it means. But for the language model, it has perfect meaning. It can tell it very precisely what to do, and can achieve that it achieves optimal performance on the task that we want to. And then when we prompt tune it, then we need to provide it a data set. We enter the soft prompt, get the prediction. We compare the prediction of the model with our target that we wanted it to predict. Then we can back propagate and update the soft prompt such that the prediction becomes better. That's like you usually do with machine learning. Just to repeat on this, the language model parameters remain frozen. When we update, when we fine-tune, we don't change the language model parameters. We only change the soft prompt matrix. And there are some additional hyperparameters that we can optimize here. So whereas, for example, the size of the soft prompt that we can change. If we have a larger soft prompt, we can usually solve more complex problems. But if we have a very simple problem, it's usually better to use a smaller soft prompt. And also, we can change how we initialize the soft prompt. But if you're curious about that, we can talk about that later. And then, exactly what I mentioned before, we only change very few parameters. So the soft prompt is usually about 0.01% of the size of the language model. And it improves us to have more generalizability and to not forget what we learned during pre-training. Now, however, there are different ways of approaching this. The most classical, the most common way of doing it is to do prompt tuning with text-to-text classification. So that basically means that we ask the model, hey, given this company description, please tell me what sector it falls into. and then the model generates the sector sequentially. Let's say first one sector, then the other one. However, one problem is that the example that Armin gave was quite simple earlier with automotives and retail, but our sectors are much, much more difficult, unfortunately. And for example, the model would just generate a sector name that is similar maybe to the original one even, but it's not the same. So it would say zero waste economy instead of circular economy. And that we can't do anything with that because we would need to use a lot of additional logic to make up for that. And even if we would provide the correct sector taxonomy, unfortunately, the model is still not able to repeat the correct sector name. So this was one big problem. Then the other problems are more technical under the hood. First of all is that when we fine-tune, when we parameter efficient fine-tune this, we need to provide the correct sectors in a specific order to do the back propagation and gradient updates. And in reality, however, there is no logical order to it. It could be sector 1, sector 2. It could also be sector 2, sector 1. And if we provide one order, the language model correctly predicts another order, then we would punish the model for predicting the correct sectors in the wrong order. So that's a problem with text-to-text classification. And another problem is that the model only tells us it's this sector or this sector, but it doesn't give us probabilities. What usually is much better to use if the model gives us probabilities. So for example, it's this sector with a probability of 90% or this sector with a probability of 60%. And then we can adjust. If we have a use case where we want to be really sure about it, we can only use the ones with 99%. If we have a use case where we rather want to find everything that might somehow belong in the sectors, we can use all the ones that are predicted with a probability of 50%. And this is why we adjusted this. And instead of using a language head, we replaced this with a classification head. So instead of actually generating language and generating the names of the sector, we replaced this with a simple classification head, which is very common in machine learning, where we basically predict a vector, and each number in this vector then refers to one sector in our sector taxonomy, and the value is the probability. So here we see that there's one with 93%, which would probably be predicted then. And this classification head is then also some additional parameters that we need to fine-tune together with the soft prompt. We conducted a couple of different experiments there. First is Android prompting, which is what Armin actually just showed us, where we have a couple of examples, and then we ask it what sector does this company belong to. Another one is only a classification head without prompt tuning, which is a very old school way of doing it, where we have the language model to generate an embedding of the company description. We feed it through a classification head and we get the predictions. Also vector similarity, which is kind of like a vector search method where we get an embedding of the company description, and our training set, we have the embeddings of those. And then we use, for example, k-nearest neighbors to get the companies with the most similar embeddings and predict the labels of those companies. And then we have prompt tuning, by which we mean prompt tuning with text-to-text classification, because that's the common way of doing it. And we have p-tech, which is prompt-tuned embedding classification. To go into the results, we see here on this graph that on this axis we see that the best performance is the highest, and on the x-axis we see that the more we go to the right, the more computation our model uses, because we were also very interested in actually how many computational resources does the model use. And we can very clearly see, we also, by the way, we experimented with two models, Llama, which was the best model that was open source at the time we started the experiment, and Bloom, which is a little bit of an older model, but the benefit it has a 1.7 billion parameter version, which is very small and enables to run quick experiments. And we can see that for both models, PTEC performed the best, and it was still more efficient than other prompt tuning methods and also than NShot especially. We can see that some easier models like KNN, classification head, and so on, were very parameter efficient. I mean, they were very computationally efficient, but they didn't perform that well. And we can see that prompt tuning with text classification didn't perform that well because of the challenges that I showed earlier. And they use slightly more computation. And we can explain that actually. If we look here, we only need to predict one vector. If we use PTEC, we only need to predict one vector, which is quite quick. But if we actually generate the labels, as we can see here, we need to generate a token by token. And basically for each token, we need to predict one vector again. So for example, to make this prediction here, we need to have at least five vectors predicted. So that's why it takes up more computation than actually this method. Exactly, and actually NShot prompting, it performed the worst, and also it required much more computation, which is because if we look at this example here, we need to provide all the examples in the context. And if the context is bigger, the language model will also need more computation to perform. And this is why this was actually the worst performing when we looked at how much computation it actually uses. And our task was much too difficult for it anyways. Exactly. And then last, we can also see on this graph, it's basically on the x-axis, we see how often we predict something incorrectly. On the y-axis, we can see how often we predict something correctly. And we want to have good performance, we want to be in the top right corner. And the PTEC model goes quite fine to that corner, while the other models are further down. And prompt tuning, which is abbreviated with PT here, the thing is, as I explained earlier, since we don't have these probabilities returned, we can't even draw this curve, but we can only give it 1 point in the graph because it doesn't allow us to adjust the probabilities to the needs of our problem. And with that, we concluded that LLMs, they still lack the long tail knowledge of these very specific niche areas. And it's very helpful to adapt them to your domain specific task. But fine tuning itself has a lot of drawbacks, and these PEFT methods can be very helpful there. And by the way, we also submitted this to a conference and published it as a preprint. If you're curious to read more about the details there, you're welcome to scan this QR code. Yeah, thank you very much for the attention. And I'm very happy to hear more questions. We also have this microphone. Armin has the microphone. There was a question here in the front, I believe.
Now it works.
How did you measure the total floating points for the experiment?
Thank you. That's a good question. I love it. It wasn't that easy, but there's a library. I forgot how it's called. It's I think it's built in PyTorch, but you might need to get, you might need to install a specific version of PyTorch. But there's a build in PyTorch that can measure it. But we actually had to, because measuring this actually takes up even a lot more computation. And so we had to like measuring it on a test run on only very small amount of data. And then we had to extrapolate that to our complete training and inference setup.
Right, thank you.
Just a random question. When it comes to the classification head, have you tried to see what is the precision of throwing something into the system and see what the system predicts versus what your existing classification is?
You mean without prompt tuning?
Yes.
Yes, that was actually the classification head experiment. So it was, I'm not sure if that's your question, but it's basically we just have the company embedding without any prompt tuning, and we feed that into the language and the classification head.
No, sorry. I was thinking, you have your classification that has been done by human beings, okay? What is the result of actually predicting some classification with LLM versus what human beings?
Yeah, thank you so much for
Yeah.
that question. For that, on this this graph, we can see the macro F1 score, which is a very abstract measure, and it's very difficult to concretely say this means this. But it basically means it relates to how often we predict something correctly for all, averaged over all sectors. Because the problem was that we had a lot of data for some sectors and very few data for some other sectors. And if you just train machine learning by default on this data, it would perform very well on those sectors with a lot of data and very bad on those sectors with very few data. And if we would use a normal metric like accuracy, then we would have a very high score, but we would only be able to predict those couple of sectors, and on all the other sectors, it wouldn't work well. So this macro F1 score kind of gives a balanced overview of how well we perform on average over all the sectors. It goes from 0 to 1. Yeah, and so we can see it as a percentage, but we have to see that we also tested to have a human label it and another human label it. And for that, the measure of agreement was also about 40%. So even two humans on that task didn't agree most of the time.
Sorry, just a question about the soft prompt. Could you please explain that with an example? It was really interesting. Was that a hyperparameter or?
The soft prompt?
Yeah.
It's not a hyperparameter. We can see it as additional model parameters. So, so here I have this example where we tokenize the input text, and then we embed this input text to get this embedding matrix. And depends on which model we use, but let's say these each embedding for each token has a length of 1000. So we have 1000 numbers representing one token. This is one row in this matrix that is shown here. And then we get one of these vectors for each of the tokens. And this is then the matrix of dimensionally 1000 times the length of the sequence. And then we add a soft prompt. Important about the soft prompt actually is that it also has a dimensionality of 1000 times the length that we set as the soft prompt length. and that is a hyperparameter. And since both of those matrices have a dimensionality of 1000 times x, we can simply stack them on top of each other to have one large matrix and then feed it together in the language model. And since in the soft prompt it has a dimensionality of 1000, we could even say that each row in the soft prompt is also a token. And so that's why they're also called virtual tokens. Just the thing is that if we would see if this row in the soft prompt exists in our embedding table, we wouldn't be able to match it to a specific token in our vocabulary, which is why we'd not be able to say what this means in human language. But it would kind of serve to the language model as an instruction of what it should do.
Thank you. And just another question about when you want to fine-tune the models, how do you know which layers to freeze and which layers to basically fine-tune? Do you just look at your data and your task that you want to do and kind of reason, or how do you think?
Yeah.
You want to fine-tune the layers?
Well, that also now here depends on which parameter-efficient fine-tuning technique you use. If you use prompt tuning, you freeze the complete large language model, and you only fine-tune the soft prompt. So you don't actually update any parameters of the language model, but only you add additional parameters in the soft prompt. But there are some other techniques where you can also update specific layers of the language model, but then we usually specify it. But then also you can often use your domain knowledge in that. For example, in this problem with the classification head, we also realized that we needed different learning rates for the soft prompt and the classification head. Because one of them was learning very fast, one of them was learning very slow, so we had to balance it out.
Thank you.
There's a question here.
Thank you so much. Thank you for the presentation. It's really insightful because I was doing master thesis this year, and I feel like my topic is like 90% similar to yours. So like your content, I feel I can relate so much. And the questions from me, there are two questions. The first is in my own master thesis, we used hard prompts. As you may know, the prompts are like human languages instead of the continuous embeddings here. And the decision we made at that time is just because we found out even if we used the soft prompts at that time, maybe inference-wise, it's faster or it doesn't make a difference, but training-wise, using soft prompts while freezing all the language model can't make the fine-tuning process faster, because to derive the gradients of the original embeddings, you still need to have to go through the whole model from the very end to the beginning to get the gradients. So I don't know if it is a trouble when you are writing the thesis in the training process. And the second question is that I'm a little bit curious about the tricks you use to initialize the soft prompts, because I feel like the way you initialize them can more or less influence the results as well. So thank you so much.
No worries. First question. Indeed, hard prompts, of course, will be much easier. It's you will need much less computation, right? But also, I mean, especially if we look at this graph here, right? We can see just that prompt tuning can achieve the same performance as full model fine tuning, while we wouldn't have been able to do that if we would have a hard prompt. just to explain to everybody, also hard prompt is if I prompt it with natural language, like in prompt engineering, right? And this, of course, we would have saved a lot of computation, but we wanted to prioritize performance on this task, since the task was already very difficult in the first place. The second question, exactly. I actually had it on the slide before, but I took it out because it was I thought it was too complex for introducing this topic. But we did 3 different experiments. Once we randomly initialized the soft prompt. Once we initiated the soft prompts with tokens that were randomly drawn from the vocabulary. And once we initialized the soft prompt with tokens from the target classes that it's supposed to predict. To explain to everybody, how we initialize the soft prompt is how we set the initial values in this soft prompt matrix before we start updating and fine-tuning them to perform good at our task. And once we initialize them with actually tokens from the vocabulary, it starts performing much better since the embedding space is very sparse. And if we already are in that kind of embedding space that has meaning for the language model, we can achieve better performance with less learning. And then updating, eventually we initialized it with tokens randomly drawn from the possible target tokens. And that improved performance an additional small amount, not much more than if we would take any random tokens, but a little bit more. So we ended up doing that. But to explain to everybody, even though we initialize it with those tokens, once we update it, the embedding, like those virtual embeddings in the soft prompt change. So after we update it, it is not similar, like it's not the same as the embeddings of the tokens in the vocabulary anymore. Thank you so much for the question. Otherwise, I would also say we are quite a bit over time, and I don't want to have anyone staying longer than we would.
Should we do one more, last one? Yep.
Thanks for the talk. Have you looked into the embedding space when you combining like soft prompt and token embeddings? And have you tried other methods other than concatenating these two?
Those are 2 really good things to look into. There are some other methods where, for example, they first pass the soft prompt through a multi-layer perceptron, just like 2 layers of a neural network to counteract some disadvantages that can occur. And what was your first question again?
Mapping to another,
yeah. There was also another paper that investigated that, but it was not very successful. So we read about that, and it didn't seem like the most promising to give additional improvements or so, because other people have done that, and it didn't seem like they were so excited about it. It didn't promise the best results, so we didn't further look into that.
But I mean, when you have trained the soft prompt parameters, have you looked into if similar classes are like clusters in the embedding space in the sense?
We have not, but one other paper has talked about this. I think maybe even 2, but they looked into it and they could not get any kind of meaning or clustering out of it. Some very vague information, but nothing that would be useful for them or provide additional insights. It did kind of show that you can more or less map those virtual tokens after fine-tuning to some area where they have some sort of meaning, but it's very unstable.
Thank you so much.
Cool. I think we end it here. Maybe another round of applause to Valentin. Amazing work.
Thank you.
And that's it for today. I hope you had a informative session, and look forward to seeing you at the next one again. Thank you.